So let's start with some really important announcements because we're wrapping up this week, which is exciting but also scary. So let's talk about the actual process of submitting the games and making sure that you have built everything that you need to in preparation for that. So what that's actually going to look like is, so the book, one of the last chapters of the book, I think that's the second or the last chapter, is about actually publishing, creating an actual build of your game. So that is what you are going to do. You're going to make a Windows build and a Mac build. There has also been request for a Linux build. So if you can get all three of those, that would be great. I will grade based on a Windows and Mac, since that's what most people in here are able to run. It's either a Windows or a Mac, but if you can get Linux out there, there are a couple of people who would really appreciate being able to play it on Linux. I haven't historically required it, but Unity now runs much better on Linux than it has historically. So it does make more sense to produce an actual Linux build. So it should just be an export to do that. You shouldn't need to do anything fancy, but getting it to work on GitHub is another problem because of all of the large files. So if anyone has ever played around with Git LFS, anyone familiar with Git LFS? One person? It's just large file structure, so it stands for large files. So you're going to state something like, we're not going to upload this to GitHub, but in order for this project to be clonable or runnable, it needs to pull that material from a local machine that has that file stored on it. So that's how you're going to store your GitHub projects. If you need it to be just something that can be downloaded directly, then you may need to link it from an external site. It is annoying to do that because you should just be able to do it off GitHub, but try to make it work to the best of your ability to just be a download off GitHub. But if you run into large file issues that Git LFS isn't solving for you, then it is acceptable to host it somewhere else and then link to that in the GitHub. I just want to avoid that if we can help it. So that's what you're going to give a public link to the GitHub, and that's going to be your submission, is here's where to go download and get the game. As part of that, you should have a README put together that are instructions for how to download and launch the game. Because these are Unity projects, that should be relatively straightforward. Download the game, extract the game, open this folder, launch this executable, play the game. So you shouldn't need a ton of effort or time put into that README, but it is very useful to just have a professional looking support for the game that you've made. Got it.
Does it count for both Windows and Mac if we just make it like a HTML5?
You just run it from the browser.
Yeah.
I would prefer to have the Windows and Linux support, because then
Okay.
what is hosting the, would it be directly off GitHub? Are you creating your own?
Well, probably my own, probably
Server.
my server.
Yeah. So I would say that is, well, you're more than welcome to do that, but I think we need the ability, just to be fair across everyone, to submit via both a Windows build and a Mac build. Other questions about submission? Does that cover everything that people feel like you need in order to be able to submit?
Don't you need Mac hyper to be able to produce the Mac build?
You do need, yeah, you do need a Mac computer to be able to do that. So if no one in your group has a Mac or no one in your group has a Windows machine, then we'll need to find someone who does, so that you can produce that.
I believe on Linux you can cross, I believe on Linux and Windows can both cross compile.
Yeah.
So.
Yeah, wait, you said you have to have a Mac to make a Mac build.
Or
Yeah,
you
you
can
just
test
have
the Mac build first. You want to have a system to test the build to make sure that you can launch it. You can't make it with something else, but when you test it, you would have no way of knowing
There's modules for it.
does it work or not.
It says,
So-
but.
Is anyone with a Mac in here willing to meet with other groups to help them to test their builds on a Mac?
So I don't have a Mac machine, but I know that there are 30 in this building that you guys can totally use. That are in the unlocked room on the other side of the hallway. that you can just go into when there's nobody, when there's not a class in there and just build.
Okay,
Okay,
so,
Let me know if they
utilize-
don't have Unity
utilize those.
and I will go through and install Unity on all 30.
perfect. Alright, that makes way more sense than taking someone else's.
We have several Mac labs for the design department
Yeah.
and they leave their doors unlocked during the day, so just as long as there isn't a class in there, go for it.
Cool.
Yeah, you know, do you need Unity on the computer?
where is that at?
Literally on the other side of the building, towards the back, kind of like how these labs are.
Okay.
Same over there. You'll know it because you open the door and you'll see a bunch of Mac machines flying around.
Yeah, from Unity, you're actually going through the build process, so you do need it to be able to create the build.
No, but after you have the executable.
Oh, yeah. then
No,
you
after you have the executable, you don't, but I don't know if they have Unity on them.
Yeah, you wanna,
I'll have to look.
Which is with the executable and good. It's really executable.
I mean, for building it for a Mac.
Yeah.
I have to build, I think you build.
He said you could build it on.
yeah, you can build it from anywhere, but you can't test it. You can make a Mac build. So you would have to throw the Mac build on GitHub.
Well, then
and
that makes it actually a lot
Go.
easier, because then you just have to
Yeah.
grab the executable.
Make executable, so you should not need to install Unity on those machines. So I think that is good. Get that testing done early so that if there are issues with that, there's a little bit of time to work through them. This is not easily acceptable over the weekend that something is due, so if you need to go, you find an issue with your Mac build. Then you wanna test it and make sure that it actually works with a Mac machine when you can still go test it, so. We good? Any other questions or concerns going ahead of submission? Yeah,
Are you gonna possibly show us how to do it in Unity or?
I can, it really is just a menu, you go to the menu, you click build, and there's a build menu for what's the target platform? And then it does it for you,
Okay.
it's, the instructions for it are in the textbook from last quarter.
Okay.
It's literally the last chapter.
Okay.
Yeah, it's like this,
Oh, yeah.
the
Or second
to last chapter.
Okay.
The last chapter is just the recap.
The recap, yeah, there's a section for that, if anything needs to be done in more detail than that, from people trying that out and saying this doesn't work, or something of this sort, let me know and I can go over whatever needs to be gone over
Okay.
in more detail.
Are you modifying the?
Other questions about submitting games?
No.
Okay, when are we not level here?
I've decided that exam day is going to be the Wednesday of week 6, which is 2 weeks from today. My plan at the moment for next week is to not have any lecture time in class. I want to have some in-class time for playing games and writing reviews. I do recognize that asking for 8 pages of review over 1 week is quite a bit of work, especially involved with 2 hours or more of playing games before you can even start writing those reviews. So I want to dedicate our class time next week to that, to make sure that you can also ask questions as questions come up about writing the reviews, about the level of analysis that's expected. I will try to, between now and next week, write what I think would be a high scoring review and a low scoring review. I'll just write them so that you can see the difference between what I'm looking for in terms of outcomes and what I think wouldn't be good enough to meet those outcomes. Just so you get a sample of that. But I really am looking for, as I mentioned in the announcement, analytical depth first and foremost. Not just what did you experience, but why. And the why just can't be because it wasn't fun, but actually diving into the design decisions that were made in the game, being able to analyze it from a technical perspective to say, why did this work or not work? So there's a real reason behind all of the scores that you assign. And then just fairness being a great outcome for something like, did you trash the game and then give it a really high score? Did you say everything was perfect and then give it a really low score? Are you assuming that all of these games are going to be AAA quality, and so every game that you review scores low because it's not the next Elden Ring? So that's the kind of fairness. I don't want you to stifle yourself if you don't enjoy something, but just keep in mind that these are 4-week games and that the associated score that you give should represent that. Do note though that a 100 should be very possible to get. because the baseline for a perfect score is 100. So if they go above and beyond what you would expect for a particular category, maybe you can give them some extra credit. That's also okay. You can say something like, the gameplay was so good that I'm giving it 25 out of 20, and that can make up for a few of the deficiencies in a couple other areas. But the end score that you give, just make sure that you're mapping that to the A's, B's, C's, et cetera outcomes. If you give a game an 80, did it deserve a B- in the class? If you give the game a 70, did it deserve for all of the developers who developed that to not get credit for this class? That would have to be a pretty poor game, right, in order to not get the associated C+ that students need to carry it forward. Since I'm not the one doing the grades, I will be doing a pass to make sure that it's fair, but I just want to make sure from the beginning that everyone is scoring the games with that perspective in mind, that the scores need to map to the grade that you think that that game deserved based on the limitations that we have in developing.
So if a game is playable at the bare minimum, then it should be about a 75, is what you're saying.
Well, I don't know, I think playable at a bare minimum is even not necessarily a minimum viable product in terms of the outcome of a game from this class. It might be the minimum viable product from what can be interacted with, but the goal of this is to create something that is fun. If there's just no fun there, that can map to an F, honestly, because that's part of the design of a game, is not just could you do these technical things, it's can you put everything together into a package that stands alone as an experience. A shitty experience, because we only had 4 weeks to develop it, but an experience that feels like it had effort and design and thought put into what is that outcome. Is it a consistent product that feels like if we had more time, we could develop this into something that would really be enjoyable, and maybe we could sell it.
Okay, we should keep-
All right, how are we doing? We ready to jump into material? We've had these issues the last couple of weeks. People don't ask for breaks and then get upset when breaks aren't given. No double standards, ask for breaks.
We should have a break at 3 and a break at 4.
A break at 4 would leave us with,
10 minutes.
yeah, so I think we could do something like
And the
3
breakdown,
and 3:40.
Okay,
And that would be something like 45 minutes or close to 45 minutes. So if I lose track of time and I'm just way too excited about what I'm talking about, someone let me know, raise your hand. It's time for a break, or just get up and start squawking and I'll get the idea.
all right.
it's time for a break.
2:14.
Precisely.
Luckily, this is why if it's not that, then I would leave it up to the class to vote. We want to use our first break at the very beginning.
No.
When you don't vote for your own bill, that's, there's something to be said about that.
Yeah. I was joking.
Oh, I know. Me too.
Other than, what else would this be like?
All right, what do we remember from last week? Last week was a while ago.
No, it's like a whole week, so.
We remember nothing, what do we remember? What happened?
Machine learning stuff, reinforcement learning stuff.
Yes,
Yeah.
what about it? What did we go over?
Chess and tic-tac-toe. Yeah.
All right, so let's just summarize, because this is just gonna take place as a sequel to that. Recommendations, I know it's really tempting to work on games during these talks, but since there will be an exam that covers this material eventually, I highly recommend that people pay attention, because it will be useful that you do. That said, if you really need to work on your game, and that's what you want to prioritize, and you'd rather watch this lecture back at a later time, that is okay. Something that you can choose to do, but just note that you're making that decision, and that might mean that it's a little bit more difficult to engage with the material when you don't have the ability to ask questions about it.
hard to ask a video questions.
That static character won't react to what I'm saying and doing. What's
It's
wrong?
easy to ask a video question, it's just not easy to get an answer from a video.
If it did, I would really be concerned.
How often do you check the comments on your YouTube videos?
I think I get notified when they happen. I think I've received a total of 1 comment on a YouTube video over the
Okay,
entirety
we
of.
flood them with comments.
Yeah.
Start commenting questions in the YouTube comments, so you can respond to them.
We gotta get it trending.
There we go. A couple of my videos have randomly gotten a couple hundred views because someone finds them
That's.
and find that they're useful, but I don't advertise them. I don't.
You don't
throw
have to
anything out
advertise
there.
them. If people start watching them, the YouTube algorithm will advertise them for you.
Yeah, exactly. All right, so we recapped the agent environment interaction of how an agent works with its environment. We talked about MVPs as state machines and transitions in graphs. So we talked about transition probabilities as well. How likely are you to end up in a successor state, given the state that you're in? We talked about the recycling robot, about the level of battery, the actions that it could take, and probabilistically changing the amount of charge on the battery. We looked at an example of a transition graph, what that would look like. So the states were just the state of the battery, and the transitions were the actions that the robot could take. And probabilistically, you would find yourself back in the same state or in a different state. We talked about designing rewards. How do we design rewards in a reinforcement learning scenario? And it depends on exactly what you're trying to train the agent to do. If you want it to solve a maze quickly and efficiently, then you should give it a score proportional to how long it took to find its way out of the maze. And then via repeated effort, it will eventually discover some correlation between the decisions that it makes and the scores that it gets. And utilizing that, it can eventually find the optimal path. But you can design that reward based on what you want the agent to do. We talked about episodic tasks that actually end and then you restart. So something like a tic-tac-toe game ends when someone wins. The maze is terminated when you find the exit. We talked about how do we assign values for a particular run. So how do you sum the rewards in ways that allow you to figure out how good a particular run was in an episodic task? So something like, what is the reward that you have at time step 1 in a maze, time step 2 in a maze, time step 3 in a maze? It's always -1 for every step that you take until you finish the maze. So you can say that a run of this maze, the value of it was the cumulative rewards that you got across the entire episode. So if it took you 28 time steps to find the exit, then you would sum -1 times 28 and get -28 for the value of that run. If it took you 300 steps, then the return would be -300. And since -28 is higher than -300, we could say that the -28 run was better or faster or more efficient than the -300 run. And that would be what the agent uses to update its value of being in each one of these states. Then we talked about continuous tasks that don't have episodes. They aren't discrete, they're always going on. So to get the concept of a return, we use that concept of a discount rate, where we're going to prioritize things that happen in the immediate future more than anything that happens in the distant future, depending on the value of gamma. We talked about policies just being the algorithm that the agent uses to decide which action to take at a particular state. So the policy is just exactly that. Given that you're in a particular state, the agent will query the policy to say, what should the successor state be? What action should I take at this point to find myself in a new state? What are those actions? With what probability should I be taking those actions from this state? Sometimes you take a single action with probability 1. Sometimes you want to explore a bit, so you take a bunch of different potential actions weighted via some function, some probabilistic function. We use that to be able to determine what is the value of being in a particular state, given that you're following a particular policy. So if you're using a random policy and not an intelligent policy, what is the value of starting a game of tic-tac-toe against an expert? You can start to answer questions like that if you're able to figure out the value of being in a particular state. We differentiated that from action values, which is a state action pair. What is the value of having been in a state and performed a particular action in that state? That would lead you to a new state where you select a new action. And then you can query the value of back propagating that state action pair to this state action pair. So the first major challenge point that I experienced, and I've experienced a lot of people making, is the difference between the state value function and the action value function. And one is that you're trying to figure out the value of a state, one is you're trying to figure out the value of a state action pair. What's the value before I make the decision? What is the value after I make the decision? About which action is before. We talked about the Bellman equation. We talked about utilizing the Bellman equation to now set up a dynamic programming sweep of this environment. We talked about the concept of an optimal policy, being that there was no improvement that we can make to this policy that leads to a better return for episodes that are simulated via that policy. We then applied the Bellman equation to this concept. So if we can find the optimal policy, then we can use the Bellman equation to find the value of all of the states, find the value of all of these state action pairs that tell us now how good is it to be in any one of these states, given that we're already following the optimal policy. Once you're following the optimal policy, then you really get a sense of the environment that you're in. If I act in the way that is the absolute optimal way, what rewards do I get for being in particular states, choosing particular actions? And if you have that, then you have a system that has solved this problem. If you had an optimal chess playing agent, then you could use that chess's experience to figure out what is the value of being in exactly this chess state. If you're using a random policy, then that doesn't really tell you very much, because the agent isn't actively trying to win based on experience, it's just moving randomly. So the value, you can come up with a value of being in that state, but it wouldn't be particularly informative because it wouldn't be based on the best that we could do. So reinforcement learning tries to, you start out with next to nothing, you're going to evaluate the policy of working randomly, you're going to improve that policy so that it's a better policy than it was, and you're going to continue to iterate that process until you have an optimal policy. Once you have an optimal policy, then we can find the values of states, the values of state actions in ways that actually inform the true value of being in that state when you're intelligently playing the game, when you're intelligently doing whatever it is that this agent is doing. Does that make sense? Questions on kind of the summary that we've gone over so far? How do you feel about it at a high level? I'm trying to not talk about the math at all, just to get a refresh us on the intuitive. What are we doing? How are we doing it?
If you presented me this on the final, I would not feel confident in answering it. Me neither.
What is the link that is? Are the questions broad, what's going on, or the questions, I get an idea of what's going on, but I don't understand exactly how it's doing that idea?
Kind of both. Some parts I kind of feel like I know what's going on, and other parts I have no idea what's going on.
Yeah,
Could we identify what are the kinds of things that you understand and the kinds of things you don't? That would help me to be able to say, what can I focus on?
That I would need to sit down and like go over the slides.
Yeah.
Like in depth, more than just sitting in the back of the room looking at them.
Yeah,
Um,
that's fair.
but I can do that.
Any other thoughts on what
Anything
people
with
are
pictures,
struggling
I
with?
understood. The pictures helped with the I'm forgetting the name of it right now, but the state diagram thingy. Graph. I understand what's going on in that.
This-
Yeah, that I understand.
Yeah. It's very similar. we're just blowing this idea up into an ability to handle much more complicated systems. So chess has way more states than a high and low battery, but the transitions between those are still, it's exactly like this. You make a move, your opponent makes a move, and it's your turn again. What changed? How do we learn what changed? How do we set up a system that as the agent plays the game and loses the game because they're garbage at it, that they can learn something?
I guess one of the things I'm confused about is how to keep this making sense when it's something more than just a high and low battery state.
Yeah. If you can somehow zoom yourself out and look at the entire game kind of from the top down, or from the side where you're looking at the entirety of the game and not abstract yourself from being in the middle of a game. What is the structure of every possible state that you could be in? Even analyzing something for tic-tac-toe that is like that. What are all of the possible states that you could be in? Could you find a way to visualize that state space as a tree? Maybe the root of that tree is an empty board. The first transition, X has made the first move. The second transition, O has made their first move. The next transition, X has made their second move. You can envision this as a big sprawling tree of possible state spaces. Some of those will merge with each other as, you know, X moves in one place, O moves in another place, X moves in a third place. That'll merge with X moves where it moved the second time, the last game, but that's for their first move, and flips what they do for their first move and their second. That would merge to the same state. So being able to visualize a larger game in terms of that web of a state space helps you to now envision, okay, what action moves us from one state to another state? In tic-tac-toe, that's placing an X somewhere or placing an O somewhere as a transition from one board state to the next board state. And if we're trying to teach an agent to intelligently select where to do that, then we need some way of differentiating what a good move is from what a bad move is. A good move improves your chances of winning. A bad move would decrease your chance of winning. How do we come up with an estimation for the chance of winning in a particular state? Experience. We have to have played some games and determined that from this state, we've won 80% of the games that we've tried. So this is a good state to be in. Now, if I'm in another state and another game where an option is I could make an action that puts me in that state, where I have an 80% chance of winning the game, then that's a pretty good state to be in. So we can back propagate our knowledge from one state to another state that is further back in the history of the game, one fewer move. Just kind of putting that back up the tree to determine, all right, some of these branches are going to be really good, some of these branches are going to be really bad. What are those? How do we correlate the decisions of the moves that we make from how frequently we win the game? Does that help? Does that make more sense as to kind of the big picture of what we're trying to do?
Think so. I'm also not 100% sure when it comes to like the empty equations that you gave us, like 100% how they work still.
Yeah, we can certainly go over that in more detail as well. So the math for that is just how we update our approximation of how good it is to be where we are based on the next piece of data that we accrue. How do we iteratively collect that data and update the value of that state?
As long as I don't have to memorize and then write that
Yeah, no,
equation on the exam.
There will always be a sheet of notes. You can put anything on that, any equation. I will never ask you to, what is the equation for? No. It would be something like apply this equation to this idea. Be able to fill out something like the grid world table from last time, and then make some kind of conclusion from that based on what is the next step? What does this table mean? How do we interpret the data that this algorithm generated? What does that mean for the next step that we make? Something that actually utilizes it, where you have an intuitive understanding of what it means rather than can you just regurgitate it. These equations are on the internet. You can always look them up. But what differentiates someone who knows what they're doing from someone who doesn't is someone who understands what this equation is doing and can't just regurgitate it. When would you change the associated parameters of it? When will this work? When will this not work? Does the concept of a return make sense at a high level? I can start there, maybe. If I asked you, I think a potential exam type question would be something like, what is a return? Not in terms of its mathematical definition, but in terms of intuitively, what is a return? And how is the concept of a return used to train an agent?
Okay. That makes me feel less scared for the exam.
Yeah, I'm not gonna give you something that is
Here's this equation.
crazy in depth. Yeah, I'm not gonna ask you this, because again, it's just math. Once you can plug in anything for these variables, then it'll solve itself. It's just a matter of knowing, when do you apply this? What does it mean at a higher level? What is a return? Does anyone want to take a stab at that, if this was something that we're asked on a pop quiz? I never do.
Isn't a return kind of like a reward for doing well, or am I?
Yeah, it's a score that you get for being in a particular state. And if you're in an episodic task, then you can figure out, when you're done with that iteration, you can figure out how well you did. It took me this many steps to iterate the maze. I moved this far forward. I put this many packages away because I'm a package robot that puts away and organizes and stores boxes.
Like time trial.
Yeah, so it'd be something like, how many steps did it take? It's a way of scoring an episode that already occurred. You could also, at any particular time, get an estimate for what the return for this episode is going to be, because historically, when you've been here before, how long has it taken you on average to terminate the episode? If you're in the middle of a maze and I have 100 instances of having been at exactly this point, I could just average my entire history for all of those other 100 episodes. How long did it take me to get from this point to the end of the maze? You can start to estimate that. Is that exactly how long it's going to take? Not necessarily, but your history would inform whether you're in a good position or a bad position based on how long does it take to finish the episode from here. Something like that. For a continuous task, though, there's no endpoint. There's no point at which you say, all right, the process terminated, I get a score for that. If this is responsible for stock trading, you can say something like, I can anticipate over the next year, the market will perform, my algorithm for market will perform at a rate that gives me, I don't know, a 20% return on investment. Based on historical market trends, based on the algorithm that I'm applying to automatically buy and sell, I can expect to get a 20% return over the next year. And you would then use that to train an algorithm for when you would buy and sell to try to maximize that return over some period of time. But you can imagine two different algorithms, one of which is a very risky algorithm, where it's possible that you lose a lot of money and then have to slowly gain the money back over a long period of time. Maybe you see that the return that you're going to get is pushed very far into the future. The concept of this discount factor or discount rate says that that is a worse outcome than getting that level of money up front, or even less money than that up front, depending on how the math works out. So the concept of a discount rate is just the extent to which getting a reward in the future matters proportionally to getting a reward now. What else can I clarify? I don't want to just jump into new material while people are confused, and because it will all build on a knowledge of kind of this background work. So I want to take the time to explain as much of this as I can so that we're all as close to on the same page as we can be. Are there other areas where we feel you're gonna stop me where there's some confusion? What is a state value function trying to do?
It's trying to evaluate, or it's trying to give every state of the game a value.
Yeah. And that value would be, how good is it to be at this position? So it becomes an estimate for the return expected between this point and the end of an episode, or from this point forever. Because that, if you have a discount factor, it's just gonna create an exponential decay in the new value of a reward. If I say that something like, because there is inflation, the value of what you are currently worth, if you don't invest and keep up with inflation, your net value gets lower and lower and lower and lower and lower the further into the future we look. So the time value of money just decays exponentially. Eventually, if I did something like, I'm gonna give you $5 a day for the rest of your life. The $5 that you get today is significantly more valuable than the $5 you get in 80 years. Just because of, you don't have the ability to invest it, you don't have the ability to spend it on something that accrues value between now and then. And the value of $5 will just straight up be less than because of inflation. So we would come up with a discount factor that appropriately maps the value of $5 at that time compared to the value of $5 today. And you use that as an exponential decay function that actually shows that, oh no, this is a one Zoom. All right. Anything else? Anything else on here? So that's a state value. What's the difference between a state value and an action value? If I were to ask you a question like that, could we describe the difference between a state value function and an action value function?
On paper, yes, but well, in words, yes, in equations, probably.
Yeah, it's fine to do it in words because the words will map to the differences that are there in the equations. So I think that starting at the intuitive level is really important.
Because an action value function is calculating the value of taking an action versus the state is calculating the value of the current state, right?
Yeah, it's the value of a state before we make a decision on the action. The value of an action, because there's still a step of what state we end up in probabilistically after we take that action. Something like you play chess, you go, I don't know, knight to e4, and your opponent still needs to react to that before it's your turn again. So the state would be, before you selected to move your knight to e4, what was the value of being in that position, according to the best actions that you could take, or a policy that might probabilistically choose some actions in that state. A state action, an action value function of that would say, now I've decided on the action knight to e4. My opponent hasn't yet responded to that. I don't yet know how my opponent will respond to that, but assuming that I've made that move, now how good is it to be? What can I expect the return to be from here? How likely am I to win the game given that I've already chosen to make this move? But the opponent hasn't responded to it yet. And there are different reasons why you might care to look at state value functions or action value functions, depending on the environment that you're in. When you have decision points, how optimal your policy is at that point. If you're using a random policy, a state action pair doesn't tell you very much because who knows why you picked the action you did. There's no reasoning behind it. You picked it randomly. So analyzing how good it is to be in a state would say, I'm not very confident in my policy, so I don't want to make a bunch of decisions based on the route that I actually took from here. Since I'm acting randomly, I want to look at the average of what all of those actions do to this state, so that once I can pick a good state, then we can transition to using an action value function. To say, when we're in this state, we're always picking that action, or very frequently picking that action. So now I can get a better sense of the value of this state, knowing that I've changed my policy to better pick actions that will lead to higher chances to win the game, higher rewards in general if it's not a game. The next question I might ask is something like, how does the Bellman equation relate to this? How does the Bellman equation make this process better or easier? How does the Bellman equation reduce the complexity of this space? First of all, how large is the state space? We'll go back to tic-tac-toe as an example. You're at the root of the tree that is all of the states of tic-tac-toe. In order to have a large sample at every one of those internal nodes, you have to play an exponential number of games, which is really bad. So how do we reduce that from an exponential number of games to a polynomial number of games?
The Bellman-Ford equation.
It's by using dynamic programming. And to use dynamic programming, that means we're going to be storing partial results as we go. So we are going to be building up this view by saying, all right, we're going to start with games that are right near the end. We're going to learn that. Then we're going to backtrack and learn games that are 2 moves from the end. We're just going to start there and try to take what we learned about the moves that end the game. And then we're going to backtrack to 3 and 4 and 5, and we're going to stop training about the 1 move to the end, or 2 moves to the end, or 3 moves to the end. We're going to try to backtrack all of that material to say, we can now base the value of some state based on the value of all of these successor states that we could end up in. So if these terminate the game, then this would tell us what moves to make to terminate the game. If we learned this really well, then we could say what moves could we make to put ourselves in a position where we're 1 move away from winning the game. So we see how that's a recursive relationship, and how if you know this information, then calculating this becomes trivial. But how do we know this information if every time we play the game, we are taking a completely different path down this really large tree? How do we ever get a large sample for here? So that's the difference between an exponential approach and a polynomial approach. The exponential approach is saying that every single game we play from the beginning is going to be what is going to end up with a 1 move away from winning or losing the game, but it's a sample of 1, and it took the entire game to get there. Is there anything that we can state about the value of being in the initial state after having played the game 40 times? We took completely different paths through the game those 40 times. I would argue that we don't have a sample, a representative sample of the initial state, because we couldn't intelligently pick the next state that we went to. So we're going to start building up from the bottom and filling in this value based on these values. Filling up, so you just kind of fill up the table and store the result as you go, in a way that now we don't need to play as many games to be able to get that kind of information. We can play a polynomial number of games instead of an exponential number of games. Yeah.
Start talking about things other than like tic-tac-toe, like a 3D like action game, and you're like fighting a boss. Like it does
Okay.
the state like every single position that like each of you could possibly be in, or like.
So this would be less like an episodic. So it could be when either you or the boss are defeated, then that ends that episode. But yeah, you could easily utilize this in terms of something like the relative health values of you and the boss, the number of items that you have that could restore your health. All of those are actions that you can take in a particular point in time. So discretizing this down into, I'm going to make a decision every 10th of a second, something like this. You could decide to, given the value of what's on the screen, should I move left, move right, move forward, move back, dodge, roll, or attack? And so you would learn relative positions, like if I choose to attack and I'm nowhere near the enemy, then I don't make any change in their health. And it leaves me open to an attack at that point. So likely it means that I'm going to reduce my health for the value of not being able to do any damage to the boss. So it can learn relatively quickly that that's a bad thing to do. So you have to be close to the boss in order to melee the boss. Great, so now that we've made that conclusion, we will, if we're far enough away from the boss, move toward the boss. If you're not turned to face the boss, turn to face the boss and then move toward the boss. When you get to the boss, maybe you've lost most of your HP because you weren't dodging the attacks as you move toward the boss. So that's a challenge of reinforcement learning of, can you even find a way to end the episode? Because to deal damage to the boss, you have to be close enough to the boss. But it looks like, depending on how you set up the reward system, that getting to the boss means that I die faster. So maybe it never learns how to defeat the boss just because it can't terminate an episode in a way that is successful. So in this case, you want to design a reward that is based on the amount of HP that you took off of the boss when you died. And that way, if you bum rush the boss and do a little bit of damage to the boss and lose very quickly, that's still better than an episode that took 10 minutes to finish and you dodged a bunch of attacks from the boss, but you never hit the boss. Since you did more damage when you died, it's a better episode. So now you would learn that, all right, I can do more damage to the boss if I can dodge its abilities as I get closer to the boss. I can hit it a few more times before I perish. And that's an even better result. So just this is like winning and losing tic-tac-toe in a bunch of different ways. It's now just a much larger state space, but you can see that the action space is still very limited, where every 10th of a second, you can imagine having control of a particular controller and saying, I'm gonna choose to move right, turn right. I'm gonna choose to move forward. I can choose to strafe or dodge roll, or whatever the actual action system is. That's a great point. It's better to use other examples than just the same game over and over. Does that tie in or make sense as to how a mapping to a discrete game on paper would map to something like an agent playing a video game?
Doesn't that end up making it like the space be like massive for like a 3D
Yeah.
game like that, where it's like, if those are all your different actions, they can make it every 10th of a section.
Right.
Or second.
So, yeah, the state space is massive. So this was a big block to reinforcement learning for a long time, until deep nets became a thing. Combining reinforcement learning with supervised learning allows you to be able to map functionally which states are close to each other. When can I learn from being in an equivalent state? If the boss is making some big ranged attack on me, it doesn't matter where I am. The correct thing is dodge. It doesn't matter if I'm close to the end of the boss or far away from the boss. Those two states are equivalent or close to equivalent when the boss is actively performing a ranged attack. So sometimes you need something like a deep net to be able to state that in a massive state space. But you could also do something like figure out, okay, I can reduce this state space by saying, I'm gonna discretize, instead of saying exactly how far away from the boss you are as a real value number, discretize it. I'm far, medium, or close. And that way, when you make a decision about moving every 10th of a second, you could now say, my goal, my current short-term goal is getting from far from the boss to medium from the boss. And that could be overridden at any point in time where the boss is attacking you. That becomes a higher priority because it leads to losing. So now you will dodge that attack and then go back to the last thing you were trying to do, which is get closer to the boss. So you can still make it a reasonably discretized space, even in something that seems like it has an infinite state space, by discretizing real values into smaller values. And even if that was too much of a state space, far and close.
Yeah. That makes sense.
Danger and not danger, basically become your labels for that. Great questions.
So how would you implement this as like software?
Basically, you're gonna have an agent that is a program, and now you just define a list of possible actions. You define the state space, and you define the transitions. You would then come up with a policy. Start with a random policy, because you don't know how to intelligently create a policy. So you will say just act randomly, and now you will just start simulating and collecting data. So now this agent takes random actions at all points in time. If you've designed a reward function for that, then it will be able to calculate the return by applying these functions for that based on the environment that you're in, and get every time it makes some sequence of decisions, it'll get some real valued reward from that sequence. As it has a history of doing that, now we can say something like, try to optimize your reward. The goal of this agent, you get a reward at the end of an episode if you are based on that reward value. So it will, without anything else, just start to learn, if you have made this state space, what is the value of being in each one of those states? Now we can apply one of these algorithms, like when we talk about iterative policy evaluation, which we just talked about at the end of last time with regards to this grid world. This is the algorithm for doing that. So it would say something like, the input to this is the policy to be evaluated. So we have an associated state space, we have a policy that says for each state, what is the probability of performing each action while in that state? What is the probability of each successor state given that you made that action in that state? All of that information is input via the amount of training that you've done so far. So we now also need a threshold for what termination looks like. When does the change become so small that we stop caring about it? And the rest of this is just code. We have variables and then we have values. So this says the change that we have seen is 0. Loop for each state in our set of states. We're going to set v to be the value of that state. We're now going to update the value of that state based on the equation from before, based on this new information that we're getting from this run. So we're going to, well, we're looking at and saying, based on this policy, what are all of the possible successor states that we could be in? What is the probability of arriving in those states? Backtrack all of that into a value for this state, and then update the value of that state. Then we're going to say that the new value of the change is the maximum of what it already was, and this difference of what the difference that we made to the value of that state. So maybe we find that we win from this state, and that leads us to increase the value of this state. Then we want to back propagate that now into saying this is the largest change that we've made so far. Great. Until this, what terminates this loop is when the changes that we make are less than that threshold. So we just continue to loop that process until it terminates, which allows us to do something. This was the example that we saw for this. We wanted to figure out the value of being in each one of these states if the goal was to reach one of these locations. If we start with a policy that is a truly random policy, then what do we do with that? It's not an intelligent policy, but we can still answer intelligent questions like, on average, how long does it take for us to terminate the episode, given that we're in a particular state? So we iteratively did that. This was this loop that we talked about. Each one of these loops is saying, after the first pass through that loop, the second pass through that loop, the third pass through that loop, the 10th pass through that loop, you start to get a better and better approximation for the value of being in these states, until if we did this forever, they would converge to this value. But in practice, we're doing this until the changes that we make to these states are so small that they're irrelevant to us. It has converged to a point where further iteration, the knowledge that we would gain from that is not enough to need to continue doing this process. We have a good enough approximation. So this gives us the values of being in each one of these states. Each one of these is a state value pair. The value of being in this state, according to this policy where we're going to move randomly, is -14. The expectation is it will take us an average of 14 transitions to terminate from here. Really, it should be 1. All we do is always left. And it should be 1. But that would be a better policy. So we need to find that policy so that we can use that policy. We're searching through a policy space at this point for how can we change acting randomly to be more intelligent. And we get that by just simulating, by doing this randomly, what is the value of being in each one of these? I now have a choice, assuming that I'm in a state that has value -14, of transitioning to a state that has value 0, a state that has value -20, a state that has value -14, or a state that has value -18. What do we prefer of those 4 options? The largest one, 0. So instead of 25% of the time doing any particular action, acting randomly, we can decide that this state's action should be always left. Then we go from a value of -14 to a value of -1, the cost of the transition to get there. So we can improve on the policy that we're already seeing by saying we now understand this policy, how this policy works in this world. We understand the value of applying this policy to this world. How can we change the policy so that it produces a better outcome, so that the values of these are higher? And instead of acting randomly, now we just say go left. And that is a better result than saying go random. So it's a back and forth process of evaluating how good is a policy and improving a policy to create a better, higher scoring situation, yeah.
So in practice, and actually program. We need to be noting and implementing all of these policies, or is there?
Yes,
Okay,
well, you'd start with a random policy, but you don't have to change the policy yourself. The policy that comes with the result of this process is just analyzing this process, saying take the maximum of the possible successor states. Now, always do that.
okay, so is there like a programmatic way, like can store these potential policies at on its own?
Yeah, so it actually will go through
Okay,
policy improvement or policy, yeah, it's policy iteration. So this is it. There's the policy evaluation component, which is what we just talked about, and the policy improvement that we're about to talk about. So now you get, this is an expectation maximization algorithm, if any of you have heard of EM or seen that in any machine learning course that you've been in. But it's evaluate, improve, evaluate, improve, evaluate, improve, continue to do that process until you go through the evaluate and improve step and it doesn't change your policy.
Perhaps now is a good time to take a break, right before we talk about that.
It is just about 3 o'clock, isn't it?
Yeah.
So let's do that. Let's take a quick 7-minute break. We'll be back at 3:05. Let's do that.
I knew there was people eating pizza, but I looked over and I saw a crowd of people, and I was like, no. I don't think I wanna go.
4 o'clock would be a little bit.
I want them just really to do the one break, you know, pizza. Get free.
This was at 12 o'clock,
Oh,
so I was like, looked over, massive crowd of people, and yeah, I don't think I would.
All right, let's get back into it. What are the next questions that people have? Is everything so far, is it starting to click, starting to make sense? Are there places where we could use a little bit more emphasis, explanation in a different way? That question saying, explain it without tic-tac-toe helps me a lot to say, all right, that example's not working well, or it's not generalizing. What example? Okay, what can I further clarify or go over?
I didn't know. That was either.
Okay.
Is this concept of policy evaluation in this example make sense? Exactly what we are doing, we're saying, after 1 step, what's the value of all of the states? After 2 steps, what's the value of all the states? After 3 steps, what's the value of all the states? And you continue to do this until it doesn't convert, until it converges to a value that you're not making enough of a change to.
Is a step like one completion? Or is a step
No,
just
it's
one?
more like we're non-deterministically in all of these states at the same time.
Okay,
We make a decision about, okay, what is the reward, what is the average reward we're going to get? By following this policy, looking 1 step ahead. I'm gonna set the value of this state to be that, and then just do that for every single state, and then update those values. And then do that again and again and again. You continue to loop this process, looking at every state, saying, what is the actual value of being in this based on the estimates of the values that I have for every other state? And then eventually this converges to the values of k equals infinity down in the lower right. Once we have that, we can now go through the process of policy improvement. So evaluation is just about getting values for states. Once we have those values for states, we can start to think about making an informed decision about where to go when we find ourselves in one of those states. So before, we used to use a random policy and we could end up in 4 different states here that have different values. It's a better policy to just greedily choose the state that maximizes your return. So we could turn this policy into this policy and we would get a better result, a better return than if we use this policy. This policy in this state is a better policy than that policy. So if we do that, then if we turn this policy into that policy. And this policy is a strict improvement over this policy. In every single state, it will take fewer steps on average to converge to one of the terminating states. we could go through this process again and evaluate this new policy. But if we did that, we would find that we didn't need to make any changes. So it converges really quickly into an optimal policy. It's just the evaluation step can take a long time to converge, but once it converges, bam, you have the optimal policy more often than not. That said, if you find your evaluation taking so long and not terminating, you can actually turn this into the expectation maximization that we see with the actual policy iteration. So the idea is, don't wait for this to fully converge. Just go some number of steps. Maybe simulate 100 steps or 1,000 steps, or have a very large threshold for termination. Does that mean that you're gonna have fully evaluated that policy? No, but you have an approximation for the value of that policy. Then you go through the improvement, and now you're collecting data on the improved policy instead of the old policy. So if you can find a way to improve the policy and collect data on an improved policy, then it will terminate faster and faster and faster and faster, to the point where you actually get out to this optimal step. If you were just trying to evaluate and finish evaluating here, this process might not be done by the time you give yourself an actual lower threshold here, and you can ping to this, done. By the time this would still be evaluated. If that makes sense. So we turn this into an expectation maximization algorithm, where we initialize values randomly, and a policy arbitrarily will evaluate that random policy, will improve that random policy, but we're not gonna spend too much time in the evaluation step. We're gonna spend some time here, doesn't matter if it's fully converted. We're going to then improve it. After we've improved it, we're gonna go back to evaluate that policy. Maybe a few changes are needed, so we'll improve it. And in very few iterations here, it will actually converge to an optimal policy that gives you optimal values, state values for all of the states in the state space. Saying that there is no policy that could improve on this. So the theoretical guarantee of this is that you end up with an optimal policy and optimal state values or state action values. Which is really cool to see that this can optimize an arbitrary process very quickly. So we call value iteration this exact process, except that, as I mentioned, we're truncating the policy evaluation. This is just saying that we're not going to wait for it to terminate, but wait for it to be sufficiently small. Instead of doing that, we're going to just update once and improve. That you can, instead of doing this even 100 or 1,000 times, just do a single step, improve the policy, single step, improve the policy, single step, improve the policy. And that converges even faster. So now you can evaluate and improve at the same time by following this. You get a nice discount factor in there, and now suddenly you can do this as a one-step process instead of waiting for the evaluation to terminate, then improving, waiting for the evaluation to terminate. Now you evaluate, improve, evaluate, improve, evaluate, improve all at once. So that's the concept of an algorithm called value iteration. That looks like that. And we just loop that process until it converges. When it converges, it will be on the optimal policy.
So would this be considered better than the policy iteration one?
Yeah, in practice, this will terminate faster.
So then what's the point of using the other one if this one's faster?
It depends on the actual application. Sometimes you really want to spend a lot of time evaluating a policy to know for sure if it's not going to learn as much from that. But in general, yeah, that's kind of the introducing that is the baseline of the reasoning for why we can combine those steps into one and do it here. So yeah, this is what's mostly used in practice. Evaluates, iterates, and evaluates, gets that optimal quickly. So value iteration is the big end step for all of this, is if you have full knowledge of your environment, then you can use value iteration to solve very quickly. Unfortunately, having a full knowledge of your environment is very frequently too good to be true. So we have to talk about what happens if we don't. So asynchronous dynamic programming is the algorithm that we're, instead of sweeping over the entire state space like we did in the grid world where we looked at every single state, we're just going to say we can update some states multiple times before we update other states. And that allows us to prioritize the updates of some states. Like for instance, if we wanted to come up with an estimate of the value of, go back to tic-tac-toe because we love it so much, starting the game of tic-tac-toe, we're not going to get very much information on that until we have knowledge of everything else. So we could choose to update the states that get us closer to winning multiple times, and that would improve the rate at which we found an optimal policy to play the game. By saying that if we can recognize that some states are more important than others when we don't know very much about the game, learning how to end the game is a very important precursor to learning how to play the game efficiently. So this is where the dynamic programming part comes in. So we've already kind of talked about it. So value iteration is also known as generalized policy iteration, which allows us to say we have an initial value function, an initial policy. We can now, we just expectation maximization, we just continue this process, evaluating, improving, evaluating, improving, evaluating, improving, until we converge. And this just works, which is wonderful. This process describes just about everything that is done in reinforcement learning in some way or another, which is great, but we don't always have full access to the environment. So we're gonna have to learn some of the parameters of the environment also through experience. And that's why we need to continue talking about more than just this, because this is what we will use, but we may need to learn some things about the environment before we can start to analyze the environment. If that makes sense. I guess we can talk about the efficiency. That's polynomial, which is great. If you're doing direct search, it's exponential. That's much better than using abstract linear algebra to try to solve linear equations. And it converges significantly faster than trying to do a large analysis of it. And if you can help it with initial values, what this says is if you have even a reasonable estimate of the value of being in a particular state, if you're trying to come up with an algorithm to make the next best chess agent, if you have a way of stating something like, here is a bunch of closing moves that are intelligent and have been well studied. Now it's not something that the system needs to learn on its own. It can just map these closing moves as something that if I find myself in one of these states where I can start applying those closing moves, apply them. And that can significantly speed up an agent that would be learning that in the first place. You're reducing the state space significantly if you can start to bias it toward a right answer. We find that reinforcement learning algorithms spend a lot of time doing stupid things, and it reaches a moment of brilliance where it solves it for the first time, or it does something by chance really intelligently, and then it can hold on to that and say, that was really good, I'm going to imitate that. But getting to that point can take a very long time. If you can give it some initial values, you can get it to that moment of brilliance sooner, which significantly speeds up the whole process.
So it's like having the solution, you're just trying to make the equation to get there.
Yeah, it would be something like, all right, you're a first-gen college student. You don't know anything about college the moment you set foot in class. But if your advisor outlined your entire first year's schedule and your entire last year's schedule, you'd have gained some knowledge and information about your degree, about what you need to do by the time you're done with your first year, so that you can work on, all right, here's where I am. I know that at the end of my junior year, I need to be in a position where these courses that were outlined for me finish off my degree. That search space is significantly smaller than you're here on your first day of college, come up with your entire degree on it, an entire 4-year plan that meets every requirement. There's a lot of research involved in that, a very large search space to come up with a degree path that makes sense. Whereas if you can be nudged in the right direction, or have the start of a plan, remember like the opening moves and the closing moves, your first year's schedule and your last year's schedule, then the distance between where you are and where you need to be is always shorter. Way fewer options to consider. You're able to learn more and faster about coming up with a good schedule if you've seen and can learn from some of that work being done for you. So this is the end of talking about dynamic programming. So everything else that we're going to talk about uses dynamic programming, but we relax some of the constraints of dynamic programming because there are many constraints on that. We need the knowledge of the environment. If we don't know anything about the world that we are in, you can imagine now being that agent that's fighting a boss in a video game. If you don't even know the world, like what causes you to lose the game, you just know I have this set of actions, go. How would you be able to make an informed decision? Imagine you're sitting there, the game is paused, and you're planning a sequence of actions to defeat the boss. But you know nothing about how those actions map to those outcomes. Can you sit and do anything efficient with regards to planning for that outcome? You don't know the causation of anything. You don't know why certain actions would map to your winning or your losing against this boss. So you need experience to be able to draw those conclusions. When I move forward directly in the line of an attack, I lose. That's not something that you can know or plan for if you don't have the experience or something that tells you when you make this action from the state, the following state has some large negative reward where you lose the game. You don't have that knowledge. So you need to generate that knowledge, accrue that knowledge via experience instead of by planning. With dynamic programming by itself, we had full knowledge of the environment, so we could just sit there and plan. Like with tic-tac-toe, you could assume that the opponent can move in any one of these spaces. I'm assuming that they're intelligent, what gets them in the best position that they could be in. You can just analyze every possible move in a small discrete game like that and plan and learn how to optimally play the game without ever having the experience of playing the game. You just analyze the game because you know the rules, you know what leads to victory. And you can come up with an intelligent policy for playing the game. Whereas most of the time in video games, we don't have that full knowledge of the environment. We need agents to have some kind of fog of war to put them on the same playing field of a player. It should have to gain information about its surroundings just like the player does. So Monte Carlo is all about learning from that experience. As you're actively playing the game, how do we update the view of the world that we are in based on the experience that we are getting? Because we don't have a message from the programming gods that is, here's the entire map. Or something like that. So it's something that we need to learn for ourselves. So Monte Carlo says that we can't just come up with the value for a policy because we don't know anything about the environment. We don't know what the possible successor states are going to be yet. We just know that maybe we made an action last time when we ended up in a state. Is that the only state we could end up in? We don't know. So you can, as you get more and more and more experience being in a particular state and making particular actions, you start to get an estimate of the value of being in that state based on the returns that you've received after having been in that state. Let me use another game for an example. We're going to go to a blackjack example. So maybe using blackjack for this would be a good example. You turn over your 2 cards, and assuming that there are enough decks that you can't count cards, you see a pair of cards that end up being the value of 14. Should you hit or should you stay? Assuming that everyone here has played blackjack or knows the rules of blackjack. Anyone raise your hand if you don't know the rules of blackjack? I can go into. So it sounds like people mostly know blackjack.
Yeah, 14 hit.
Why though? Can you analyze that, because you don't know what the opponent has, could you analyze the entirety of that state space? You actually probably could, to determine whether that's a good thing or not a good thing. But if you don't know what wins the game and loses the game, you just know at some point after you make an action, the system returns to you, you've lost. So you don't know that going over 21 is bad. Hitting 21 is great, and being less than 21 is also bad, but not as bad as going over 21. Yeah,
I think also depends on what the dealer has.
yeah, but that's unknown for you before you hit or stay. They haven't flipped over their cards yet.
Yeah.
I think they flipped over one card.
Yeah,
Yeah, so based on, yeah, you could say that the state here is based on the card that is showing there as well, for sure. But the idea is that if you played this game enough, you would have a sense of when I hit on 14, I instantly lose this proportion of. Regardless of knowing exactly what terminates the game or not, just the fact that you received that signal from the game, you lost. You would start to get a sense of a proportion of how frequently do I lose the game immediately when I get on a 14? How frequently do I get another opportunity to decide to hit or stay on whatever comes next after I hit on a 14? So you get a sense of being able to come up with the values of those states by experience. That's the point that I'm trying to draw. You can't analyze it to get a sense of it. You can get a sense of it through. One important note is that this value, in order to get that to converge, we have to consider an important concept called first visit versus every visit. That says that a simplifying assumption that can be made is the value of being in a state is the same every time you visit it, and doesn't need to be updated if you go back to a state that you've already seen before. You can imagine in, I guess, the recycling robot example, where you have a high battery and you've made the decision, I guess we'll just keep it as a state, high battery. It doesn't matter how you got there, or if you've been there 8 times before, the decision that you want to make from that state is always the same. So if you wanted to update the value of this state based on something, you could only do it based on the first time you got there. Otherwise, you'd be getting there a bunch of times, and that would create a really difficult way of coming up with the value of being in that state, because now you waited for the episode to terminate, and it was after visiting the state a bunch of times. How do you take the end result and back propagate that to the value of this state when you were in that state more times? So in first visit Monte Carlo, we're saying we're only caring about the first visit, and we'll only update the value of that state based on the first time we were in there, or we arrived there. Every visit Monte Carlo says we're going to update that value of that state every time we saw it, and that would give us a better approximation. However, that it is much harder. First visit is a much easier calculation and is usually a very good approximation. Every visit is what you really want to do if you're getting at a true theoretical probability, but we have to talk about function approximation and eligibility traces, which are so far into the book that is past what I'm planning to cover for this. So we'll focus mostly on first visit for the moment, but note there is a whole layer to this about how to update for every visit in ways that, especially in certain situations, it's valuable. Questions so far?
Not so far, but I'm sure I'll have some later.
Excellent. Anyone else? Everything making sense reasonably at an intuitive level so far?
I'm still thinking of my destiny gun.
Yes. So here's an algorithm for you for first visit Monte Carlo. The input, as always, is a policy. We want to figure out how good is this particular policy. And now we're going to say, we're going to initialize the value of states randomly. We have no information about what the value of those states are going to be. So we just randomly assign those values and say that based on the experience that we get, this will eventually converge to the real values of those states. Then we continue to loop until we decide to stop. It says loop forever, but that's because this process will never fully terminate. You just decide once you have enough experience to be able to make a conclusion, then we will stop. So we'll generate an episode. This says that we're gonna play the game once, if we're using tic-tac-toe as an example. Play a game of tic-tac-toe. If it's a game of Avatar versus boss, then we'll play one iteration until the player character dies, so like the agent character dies or the boss dies. So generate an episode, then we set the return to 0 for every step of that. We're generating that episode and then we're gonna analyze what happened, starting at the end and working our way backwards to the beginning. So let's run with this boss versus player character scenario. So maybe every 10th of a second, there was a decision made by the player character about how to handle the boss. Eventually, this episode terminated and the player character was killed. We could backtrack from the terminating episode, and we're gonna start at time t-1. What happened right before the player character was killed? We want to assign that a negative value, but we're using this concept of a discount rate, saying that with one time step before the negative reward happened. So we're actually going to multiply the negative reward by a small factor and make it less negative. So being in that state was a little bit less negative than being right there. Being in the state that was 2 steps before the player character was killed gets a little bit less of a negative reward. Until we get all the way back to the very beginning. And somehow, maybe these first few moves put us in a situation where we couldn't win the game. Because we had jumped right when an attack was coming our way. We have no way to control the player character in the air. By the time we landed, we did not have time to get out of the way before the projectile hit us and one-shot us. That would say that we're just going to slowly backtrack through the decisions that were made up to that point and assign some amount of negative value to the fact that we lost the game at time t. So that's that concept of learning through experience. We then just continue to do this. We append the return that we got to a list of returns, average that length, that return from that state, saying that maybe at time t-2, we were in a state where we have lost the game or lost the battle every single time. So we're going to state that with this new information, we're going to generate a new average of the value of that state based on our experience. Now that we have one more experience of being in that state, we're going to say that we have one more piece of data. Great. Included in an average of the value of that state for every time we've seen that state. Then we loop back around and generate another episode. We're going to have another fight. That fight, there's some decisions made and there's an outcome. Maybe the player character loses again. We'll loop through every step of that episode, backtracking the result that we lost back through every decision we made based on that discount rate and the reward that we got from losing the game, continue that process. Eventually, we generate an episode where the player character won. So we'd be back propagating a positive experience back through the decisions that were made all the way back to the beginning of that episode. So you can see that we're just playing the game over and over and over and over and over and over and over again, and eventually letting the law of large numbers kick in. To where if we have enough experience in a particular state, we can learn what the good actions and bad actions are from how frequently each action led to our winning or losing. Make sense? So we're going to talk about blackjack because blackjack's a really interesting game to talk about. So states in blackjack, we know the sum of the cards that we have in our hand. We know whether one of those cards is a usable ace that would give us 2 possible different values of what's in our hand. So we have an ace and an 8. We have a usable ace, so the value of our hand is either a 9 or a 19. So that the fact that has usable ace distinguishes you could be in 2 possible states right now. There's also the dealer's card that's showing. An action, one of 2 things, we either hit or stay or stay. A reward if we win, draw, or lose. Normally you don't allow for a draw. If you tie, the house wins. That's what makes all of the money. That one rule means you should never play blackjack. So even though the environment dynamics are completely known, it is reasonably a large search space for dynamic programming. but we could easily take a Monte Carlo approach for it. So you can see that after we've played the game 10,000 times, you get a sense of what we should do. This is what the dealer is showing. Here's what the player's sum is from 12 up to 21. And after 10,000 episodes, because we don't get very many usable aces very frequently, if you played 10,000 games of blackjack, how many times do you think you would have a usable ace within those 10,000 episodes?
I don't know, what, you have a 4 in 52 chance of pulling an ace, right?
As one of your two cards, but it could be either that card or the other card. But if you have an ace and some other, like you have an ace and a face card, you already have a 21, so why would you ever hit and choose that it's a 10? Or sorry, choose that it's an 11? So there are some things that don't really make sense, but the idea is this is a really small sample and it takes a lot of episodes for this concept to converge on the value of having a usable ace. Also because those are the longest ways to play blackjack. So let's say you have an ace and a 2. It's either 3 or 13. How many games of that would you need to play to get an example, to get a sense of, is it good to hit or stay on that 13? It's gonna take a lot of episodes because you're gonna need more cards on average to get to one of those higher values that's in a good state. So it takes a longer time to back propagate that information all the way back to that 13 because you probably hit 2 or 3 more times before you stick at that point. So that's why this doesn't have a lot there's a lot of variation in it, is it hasn't learned very much. The law of large numbers hasn't been able to kick in because we didn't see too many usable aces. At 10,000 episodes, if we didn't have a usable ace, you can see that we've mostly converged. We get a sense of how likely are we to win the game and what's the value of each one of these states based on the actual value of the hand. After 500,000 episodes, this is now 50 times more than that. We can see that we've mostly converged now on what to do when you have a usable ace. And remember that in this 3D space, even having a usable ace, now this is based on what the dealer is showing and the sum of that. So every usable ace is just one data point in here. So of course, it's not going to have converged yet. So it takes way more episodes to even remotely converge into some real values. But you're now thinking this took 500,000 simulations of playing blackjack to get that result. So it took a long time to learn. Is there any way that we could have done this faster? The answer is to force a usable ace. We said that if we can give it that nudge for learning something, we know that by the time this converges, this hasn't. So maybe make every other episode force it to have a usable ace, and that way after fewer episodes, we'd have more information about this, and a little bit less information about this wouldn't be the end of the world. So you can more intelligently utilize the number of episodes to try to train what you think is going to be difficult for the agent to learn.
I have a kind of off-topic question.
Yeah,
Have you ever heard of the YouTuber Code Bullet?
yes,
Okay,
I'm passively familiar with the name. I have not dug into too much, but
one of his things that he does a lot is write AI to beat games.
Yeah. yeah,
And one of the things he mentions a lot is running a lot of, I guess, episodes.
mhm.
And I'm curious about.
Yeah.
How
We
these,
use reinforcement learning for that, for sure. So what he's doing behind the scenes is something very similar to this. So again, dynamic programming allowed us to plan and make an informed decision about the value of this state based on all possible successor states. Monte Carlo, we're generating an entire episode from initialization to termination and then backtracking the result of the episode through all of the states that we visited in that run to update the value of those states because we have one more sample now of having been in that state. And that helps us to understand the parameters of the environment that we are in. Because we don't know them. If we did know them, it'd be better to apply dynamic programming, usually. We should probably take our second break.
Probably.
So let's do that. We'll come back at 3:45 and polish off the last 15 or 20 minutes before I think we should all go get pizza. All right, let's bring it back in.
Yeah, I would not.
Last few minutes, we got this.
I have a quick side question for you.
Yeah,
For our game, since we're gonna put you in it, do you want it to be like a professional headshot we steal from the internet, or do you want it to be like a really funny cringe picture?
whatever would make you happier.
Alright.
So
Great.
what you do is deep dive past and find something that he'll never expect.
This is something you can ask the class, and I think you can.
Get some embarrassing photos.
I asked ChatGPT, given this professional headshot, give me a baby. Pixelated baby sprite.
Give me what they would look like as a child.
Yes.
So what you do.
Maybe compare it to real baby photos and see how it did. All right, so we talked about the difference between Monte Carlo and dynamic programming. Here's a sense of what that would look like. So here's an example of a game where if we hit the final green one, we terminate with a high value. We get value 1. Here we get value -1. What is the value of being in each one of these other states? Now, we could use dynamic programming to do this, but we could also store this as just state action pairs and via experience, just generate a bunch of episodes starting with a random policy. And now we can start to see, these are the values of each state. These are the values of each state action pair. And you can see now, hopefully this also helps you to get a sense of the difference between the values of states. We're saying, how good is it to be here? And a state action, which says, how good is it to be here, having made the decision to move right? What's fun about this is that you don't always end up where you decide to move. There is some level of a chance that what you choose to do is overridden with a random action, which makes it especially difficult to learn because you decide to move right and you find yourself down. Oops. So that's why something like being here and choosing to move right doesn't give you the 1 that you would expect. The average value is 0.85. Because if you move here, great, and if you accidentally move here, suddenly you're going to be in a worse situation than you were because you're a single move away from losing the game instead of winning. But it converges given an infinite number of samples, so if you played this game forever, the actual value of being in each one of these states or being in each one of these states and choosing a particular action would converge to these values. Unfortunately, you do not have an infinite amount of time to collect data, so you need to be able to know when do we stop collecting data? When have we relatively converged to this point? And there's no real answer to that. It depends on how accurate you need it to be. I like looking at Robo Rosewater for that, to get a sense of how much training leads to what, especially for the Magic the Gathering fans in here. I've talked about Robo Rosewater, right? Once last quarter, I think.
Not enough that I remember
We
it.
talked about magic a lot, but I don't know.
Yeah,
which-
so this is a neural network that generates cards, basically. It takes in as input every Magic the Gathering card that's ever been printed, and then tries to generate new Magic the Gathering cards. And it produces, if it hasn't been trained particularly effectively, then it generates some really interesting keywords like Mointenspock. What does that mean? It's based on Mountain Walk, but it certainly took a little liberty in trying to assign value such that it came out with Mointenspock. If you train it a lot, it starts to have some really interesting decisions about real cards that could be printed. Like at one point, it came up with a color shifted lightning bolt that really felt black in nature. At other points, it generates really interesting cards that it feels like could have been actually designed in practice. So the amount of training is really important. The more data that it generates, it gets a much better idea of what are the real patterns that emerge from the sheer number of cards that have been printed historically. what helps this is if we can now not always start in the same location. Because if you always start at the same location, then you're always going to be gathering data from that location. And you won't always be exploring every possible state action pair. If you learn that it's really good when you start in this square facing this direction, that you go up and then over. It would learn that really effectively, and you don't know the value of being here and moving left. It's not a good action, but what if it were? The idea is it finds a way to solve the problem, and then it's going to really want to solve the problem that way. So to avoid that, you can use a concept called exploring starts. And this just says when you start an episode, start at a random state oriented in a random direction. And if you start randomly, then you will be picking every state action pair at some point, because there will always be an exploring start sometime in the future that puts you there as the first action that you've done. So you will get an infinite amount of experience for every state action pair, given that you run this an infinite number of times. So it gives you a nice theoretical guarantee of when this does converge, we know that it didn't converge just based off of happening upon a way to win the game and then optimizing that particular path. It tried everything. And this was still the best way that it found. Does that make sense? Alright, so now we're actually getting into how does this actually work in practice. We're doing exactly the same thing, generalized policy iteration, also the value iteration that we talked about before. We're going to start with a policy. This can be a completely random policy. And then we run a single episode in that Monte Carlo. We generate the returns, the return from that episode, we back propagate it through the states that we visited. And then we're going to improve the policy. We're going to say, based on that, if we want to change the directions of any of our actions from that point, do we change the policy based on this one episode? Great, we changed some things. We're going to go generate another episode. So we use the same idea of an expectation maximization algorithm. We're going to evaluate a policy by saying, how well did it perform on this one episode? Then we're going to improve the policy. Then we're going to generate another episode, evaluate that, improve the policy, and do this back and forth, just like before, until it converges on an optimal. So it generates an algorithm that we can write down and implement. So these are the algorithmic steps to produce a Monte Carlo learner with exploring starts. So this would be very well utilized anytime that you are you don't know the domain that you're in. You don't know what all of the actions do to lead to winning or losing, getting particular rewards. If you need to learn that from experience, then exploring starts Monte Carlo is what you want to do. At least it's one option of what to do. So going back to blackjack, we see that here is a usable ace and an unusable ace. This is the probability of hitting versus sticking. This is what it converged to via a large number of episodes. So if the dealer is showing this particular card and the sum of your cards leads to that, this is the optimal way to play blackjack, according to what this algorithm learned via simulating this hundreds of thousands of times. It's funny to think that a game that is this prevalent at a casino is this simple to solve. The outcome to what is optimal for blackjack can be displayed in these two diagrams. It kind of takes the fun out of the game. Questions on applying this to blackjack, or kind of just the solution? It solved the game. It gave you a policy that we now know to be the optimal policy because it kept generating episodes and trying to change the policy, and the policy always reverted back to this. Any deviation from this was instantly pushed back here. There is no better way to play blackjack. than that.
So if the dealer's showing a 5 and I have a 13, just stay.
Yep, dealer showing a 5, you have a 13, this says you should stick.
Alright then.
Yeah, it's because the dealer is very likely to bust. They're more likely to bust if you have anything here. So basically, as long as you're not guaranteed that another card will not bust you. If a dealer is showing a 3, 4, 5, or 6, it is so likely that the dealer will bust that you should continue to hit until there's a possibility that you could bust and then stay. Let the dealer bust is that technique. Because you are more likely to bust from this, from continuing to hit, than they are, because they have to go by a defined set of rules. They hit on 17, stick on 18. For good, or is it 16 and 17? I obviously don't,
If they have a 17, they have to hit.
yeah. I obviously don't gamble. I want to keep my money.
It's a house.
So, yeah, the house has to follow a particular rule set, given what they need to do. This is the appropriate reaction.
Yeah,
I thought they had to hit on 7.
no, it's they always stand on 17, they always hit below 17.
So. Epsilon soft, we've already talked about using this concept of epsilon to add exploration to a system. It's very similar. Instead of using exploring starts where we start at a different position every time we start an episode. Epsilon soft says we can build the exploration into our policy, and that way we can always start at the same location. We just need to differentiate between what we think is optimal to do and doing something we don't think is optimal to continue to gain information. This is why I go over all of the exploration parts of this before diving into, because having an intuition of why exploration is really important, why it's important to continue getting experience with exploratory actions is an important prerequisite to understanding why epsilon soft works so well. So now the policy has some probability of not doing what we think is optimal built into the policy. As a way of knowing that our policy is correct, that is, we need that theoretical guarantee that we have the optimal policy. We know what the best move is, and there's no way to reach that guarantee if we don't get an infinite amount of experience with every action from every state. So while we are training, at least, doing something that is epsilon soft is very useful for that training process. So with some probability epsilon, we're gonna pick some action that is not optimal. Every action has at least some probability of being selected, and then we select sometimes things that aren't optimal. So here's some pseudocode for that. We just have an associated update that we need to make for every action in our action set from a particular state. And it looks gross. Every one of these looks gross, but it really is just the concepts that we have covered so far. So this breaks down to be something that is actually relatively simple and easy to implement. I just don't want to go down into the line by line of it because that won't be relevant to people until you actually need to go implement it. Let's see. This is a very important conversation. So maybe I will introduce you to this concept and then we'll come back eventually and talk about the rest of it. So let's talk about on policy and off policy. So an on policy is saying that what we actually choose to do is based on our policy and only our policy. Off policy says we are going to be evaluating a different policy from the one that we are implementing. We're going to be generating two policies at the same time. One policy that we use to explore, and one policy that is the optimal policy that we're designing behind the scenes for when we stop training, we'll transition to using that as the final optimal policy. Does that concept make sense? So on policy would say, You have one life. What you do in your life, if it results in your death, you're kind of done. That's unfortunate, but reality. You're now, what you learn directly informs the policy that directly informs what you do. There is one policy, what you learn and what you do are the same thing. But imagine splitting that process off to, I'm going to learn something different from what I do. Now, when I am in the training phase, I can make a bunch of mistakes. I know this is stupid. I'm gonna do it anyway because I can learn from it. And what you're building when you do that is full knowledge that that is a mistake. I've tried it multiple times, it's stupid. So what you use to learn and what you use to optimize are different. So as you are going about exploring, you are making mistakes, you're getting new data, but you're optimizing something in the background for once this becomes the real time to shine, I will do what is optimal. So that's off policy. There are two different policies, the target policy and the behavior policy. So the target policy is what we are building behind the scenes in our brain. This is saying, what do we really want to do if we were going to exploit all of our knowledge that we've gained so far? The behavior policy builds in that exploration to occasionally do the suboptimal thing to continue to gather data to ensure that those are suboptimal actions. Think of it like, I know what to do, but I'm going to choose not to do it because I want to see what happens. Oops, that was a mistake. Great, that's what I thought.
So the process I go through when I play most games or there's choices like.
Yeah, it's an
this is
off-policy
what I
type
do.
of procedure. Yeah, yeah. Think of it like, if I put an exam in front of you right now for this class with minimal preparation, you would do the best that you could on it, knowing full well you're probably going to make some mistakes because you haven't trained well. If I say, this is a practice exam, and you don't want to know, do I understand this material or not? You want to understand, what is that professor's grading system? How much of a mistake can I make before he docks 1 point, or 3 points, or half the points? You could, on the practice test, because it doesn't lead to your grade, make some exploratory mistakes and see what the grade you got back from that was. And that would give you a much better understanding of the professor's grading system. With that understanding, now when I put the real exam in front of you and you think, I can either make this mistake or that mistake. And I know that it's not right no matter what I do, but I can do this or that. You utilize the experience from the practice exam to know he marks off more for this kind of mistake than that kind of mistake. I'm going to err on the side of this to be able to make this decision. And you wouldn't have been able to do that if you hadn't had the opportunity to make those mistakes in a test setting beforehand. Question? All right, this is probably where we're going to stop. We're going to come back to this as we start, because we're going to start branching our algorithms into 2 different algorithms, an on-policy learner and an off-policy learner. And we'll see what the benefits and detriments are when we learn via an on-policy environment and we learn via an off-policy environment. What are the reasons you would choose one or the other? What are they good for? So we'll do that. So Monday, I guess games are due Sunday night. Monday, we're going to be spending some time reviewing and writing up reviews. So I want to kind of set that up as this is a time to play the games and start to get a sense of that, ask questions as that happens. We'll do that as well on Wednesday. Remember that next Wednesday, a week from today, is when we decided that we're going to have our party. I sent out the invitation to Dustin. He will be here for that. So our Microsoft Games employee is gonna be here for that. I've also sent out an invitation to Inside EWU, so the entire campus will be alerted that this is happening, which is great. What I'm envisioning for that is we'll kind of set up different stations in here where people will be able to play. Game 1 is over here, game 2 is over here, something like that. People can just walk in, play a game in a station, ask questions about it, give feedback about it, and then leave whenever they want. Yeah. So that is the plan for the moment. I will send out the rest of that invitation to the rest of the department later this week.
Okay.
Any other questions? I'll have a study guide for you for the exam by next Wednesday.
So as far as submission, we're just gonna send a link from the GitHub to.
Yeah, you'll send a link to the GitHub. You'll publish a link to the GitHub, and then people will use the README on your GitHub to install the game.
Gotcha. Are you making like an assignment on Canvas for that? For us to-
Yeah. Yeah, I think that is it technically up? The review assignment is up. But yeah, there will be a place for you to actually submit your games by Sunday. And there's one person from your group that needs to submit them.
So when you submit those, will you send us the link to the games? that
I'll
we're-
probably make it, I actually probably make it a discussion post, so it won't even be an assignment, it'll be a discussion.
So you can go in and play the games that we are.
Yeah, we're gonna have the name of the game and a link to the repository, and that way. If you were assigned that game, then you'll go play it, you never have to tell anyone in that group, I was assigned your game. One of the reviews that you got from this was my review, all of that information will be redacted, and it doesn't have to be public. So they can't ever use anything to say against it. Unless you tell them that you've reviewed their game and you're the one who gave them the review star. But then at that point, you're doing it to yourself.
And I mean, genuinely surprised if anybody even tested the Mac.
Any other questions before we go get pizza?
Yes.
I have one track mind now. Alright, we'll call class a little bit early next time. I've never class in a while. Hopefully this is relevant and useful to people. You're going to see how you could put together in our allocations. Hopefully.
I don't.
We'll get to the really important. We're gonna talk about important sampling, really important bias and variance.
What?
We're gonna talk about.
Yeah, but if we're not
Getting into
either of you.
temporal difference, how temporal difference varies, and then. Really.
Yeah.
And so I said, you know, the temporal difference on policy and on policy algorithms, maybe you want to include in there.
I think that's right.
Learning algorithm, and then not call it the temporal difference algorithm. So knowing that, like knowing what's good and bad, that can inform when you want to use some difference too.
Kept it on that day, but I know that.
That is fucking
I'll that's be like, hey, we so not getting my midterm for